Next up, we have the third oral talk of this session of research papers. The speaker, please come to the stage. So this is Yuhan Zhao, right? On unlocking the hidden treasures, enhancing recommendations with unlabeled data. Please.
Hello, everyone. My name is Yuhan Zhao. Today, I will show you our recent work unlocking the hidden treasures, enhancing recommendation with unlabeled data. So this presentation includes 5 parts: backgrounds, related works, motivations, proposed method, and experiments. I want to highlight our design choice rather than concrete equations, so I hope you can enjoy this presentation. So first, let's review some fundamental definition. So CF, collaborative filtering, leverages user item interactions to model user preference. In real world, such interactions are normally implicit feedback. For example, user clicks some items. So CF has a unique data format. For a given user, their data can split as labeled data. User has interacted, normally space. Unlabeled data, user has not interacted with, normally massive. So we focus on an interesting and important problem: how to use this massive unlabeled data. So some works make an intuitive assumption that unlabeled data can directly provide negative signals, such as MF, BPR, CML, but more and more research realize that unlabeled data are different with negative samples. Let me give you an intuitive example. Here we have 3 different items that I have not interacted with. The first one is iPhone 16 Pro. It's too expensive, but I will buy it in the future. So actually, it provides a positive signal for me. And the second one is iPhone 16. It's good overall, but some features are missing. So I'm struggling whether to buy it. So actually, it provides a neutral signal. And the last one is iPhone SE. It has an old design. I don't like it. So it actually provides a negative signal. You can see 3 different items, but only one can provide real negative signals. And the mainstream idea is to select M negative items from N candidate unlabeled items using negative sampling or data filtering method. However, under these methods, the remaining data are overlooked. You can see this picture. In the left one, we have 12 different items. But after these methods, we only select 6 items to train our model. So the remaining data are overlooked. Under this situation, we pose an interesting problem. Is it feasible to fully unearth and leverage the information in massive unlabeled data? Our answer is a novel positive, neutral, negative learning paradigm. Neutral class include unlabeled data that are challenging to directly classify as negative. So first step, we classify unlabeled data to neutral or negative class. Then we model these triple relationships like this equation. So by the way, we establish a theoretical connection between PNN and one-way partial AUC to prove our methods. Due to the time limitation, if you are interested, you can see the original paper. So PNN looks good, right? But providing a concrete implementation is technical challenging for at least 2 reasons. First one, space supervised signals. Reliable signal primarily stem from user interactions, which tend to be space compared to the massive unlabeled data. So it is challenged for us to classify the unlabeled data. The second problem is traditional loss function always handles the positive, negative paradigms. But we have a triple-wise relationships to tackle. So we need to find or propose a new loss function to solve this problem. So for the first problem, we propose a Salmon supervised learning paradigm to solve. Our overall object is LU. LU includes two parts. The first one is LBPR. At the training beginning, we rely on the BPR loss to get information. And once the model have enough knowledge to classification, we want to focus on optimizing the PN loss. Because the LPN donate our triple-wise relationship loss function. So the key is parameter lambda. The lambda control which loss is the main loss. We propose a user-aware attention method to solve this problem, like this equation. Then we talk about our classification. Intuitively, the items with the lowest similarity to a user are more likely to be truly negative. So we use this equation to select the negative items. The remaining unlabeled data, we think they are neutral class. And there is an interesting problem. Our knowledge was come from BPR loss. So think this situation, item 1 and item 2 have same scores. In this situation, we are hard to classify which one is negative, which one is neutral, right? So to avoid this situation, we proposed L uniform. L uniform aims to keep all items as far away as possible. So no items have same scores to avoid this problem. Then we finish the classification and we talk about our ranking problem. To model this triple-wise relationship, let's think about an intuitive solution. How many times should we compare if we use pairwise comparison to model these relationships? The answer is the orange one. We need positive and neutral classes and negative classes, and we need to keep all positive items greater than neutral items greater than all negative samples. So it is unacceptable in real world because the neutral and negative class have so many items. So to approximate this triple-wise relationship, we propose a two-step centroid ranking approach. First step, we calculate the centroid of each classes. Then we use the L rank to model these centroid relationships. But only the first step is not work because the first step only enforces the ranking relationship on the centroids. But classes may overlap. Therefore, we want to maintain margins between different classes so that we can keep the site level property. Our insight is to utilize two clamp embedding. You can see the picture. At the picture A, we have positive item, neutral items, and negative items. We also have two clamp embedding. From A to B, the clamp embedding are contracted. So through this process, we create margin between different classes. The equation you can see in the right part, but is a little hard to understand, so I provide these figures to your easy understand. Then we talk about our experiments. First, we test our methods with different CF models. You can see with the help of PNN, all the base models have a significant performance improvement. The results confirm the superiority of our proposed PNN solution. And then we compare PNN and other SOTA methods. By the way, the base model is MF. PNN constantly shows the best performance across all data sizes. Next, we talk about our ablation study. You can see this picture. It suggests that all components positively contribute to model performance. I want to highlight 2 points. The first one is PNN without ranking. Without L ranking, we can't leverage the triple-wise ranking relations. And the second one is PNN without Simon supervised learning. If we don't use the Simon supervised learning, we have no knowledge, we have no information to classify the unlabeled data. So I want to highlight this 2 points of ablation study. And then we talk about our efficiency analysis. So we compare PNN and the other 3 models to show our efficiency, like BPR, MF, Simple X, and ANS. PNN is the second most efficiency method. With its outstanding performance, we believe it is a suitable choice for practical use. Then we summarize our works. We introduce novel PNN learning paradigms to use unlabeled data. And we establish the relation between PNN and OPAOC to prove our method. And our PNN methods can be seamlessly integrated with different CF models to improve their performance. And we perform extensive experiments and to show our performance. I'm so happy that I noticed that more and more research in RecSys realize the unlabeled data's importance. Wish more researchers would pay attention to how to use massive unlabeled data. And in the future, we want to explore the unlabeled data and the diversity. You know, we have limited positive items, but unlabeled data have different category, different information. So we hope we use unlabeled data to improve the diversity and the other metric beyond the accuracy. Yeah, thank you for your listening. If you have any question, please free to contact me by the email.
Thank you, Yuhan. We have some questions online here. Before that, do you have anyone in the audience that wants to ask a question on the mic? Okay. People are a bit shy after lunch, perhaps. Okay, there's a question from Joe Constant about the example you gave initially to motivate the work with the iPhones. He used an example, a counter example, to illustrate a potential issue here, which is the fact that, well, let me read it. In your iPhone example, your negative example was only negative compared with the other iPhones. If the system has a bunch of flip phones, even the bottom iPhone might be positive. In other words, how can your approach address the fact that negative feedback is in the context of the small subset of the content that the user actually saw? I think what he means here is, in a sense, you're identifying further positive, neutral, and negative examples based upon a small set of known feedback from the user, which is potentially biased also.
Yeah, first I want to explain that user attitude is very complex. So it's not just a positive, neutral, and negative. So maybe we have many different attitudes. And maybe, for example, iPhone 16, maybe some features are positive, maybe some features are negative, maybe some features are we don't care about. So we just stand a perspective of user, and in the future we may dig out the more complex methods to dig out their attitude. but now we only use this perspective to research. Yeah.
Okay, there are more questions on Slido, but in the interest of time, I encourage you to look them up later on the app. Let's thank the speaker again.